A car company just built a humanoid robot with technology that even Boston Dynamics hasn't touched yet. XPENG Iron carries something no other humanoid robot has ever shipped with, an all-solid-state battery. And the reason that matters isn't battery life. It's what that single engineering decision reveals about where this machine is actually headed. The humanoid robot race is accelerating faster than most people realize. Every major technology company now has a robot program. Every major manufacturer wants one on the factory floor. The machines that define this decade aren't going to be the most famous ones. They're going to be the ones quietly solving the problems nobody else bothered with. XPENG Iron might be exactly that machine. Most people know XPENG as an electric vehicle brand. That's the surface-level read. What's actually happening is that XPENG Robotics has been operating as a largely separate engineering division, pulling talent from aerospace, medical devices, and advanced manufacturing. The result is the XPENG Iron humanoid robot, 178 centimeters tall, 70 kilograms, with 82 degrees of freedom across its entire body. First revealed in 2024, updated significantly for 2025, and now targeting mass production in late 2026. For a robot that barely exists in Western tech coverage, it is doing a remarkable number of things first. Let's start with the thing that should have generated significantly more headlines than it did. XPENG Iron runs on an all-solid-state battery. That is an industry first for a humanoid robot. No other production-targeted humanoid robot, not Optimus, not Atlas, not Figure 03, ships with solid-state energy storage. The engineering implications go beyond runtime. A conventional lithium-ion battery in a humanoid robot creates real liability. Thermal instability under heavy load, swelling risk during falls or impact, and chemical hazard in environments where the robot is working directly alongside humans. Solid state eliminates the liquid electrolyte. The chemistry is stable, the energy density is higher. The safety profile in close proximity operation is dramatically better. XPENG claims 4 hours of runtime from this pack. That's respectable. But the real argument for this decision isn't endurance, it's deployment environment. A humanoid robot solid-state battery combination makes certification for human-occupied workspaces substantially easier to achieve. The hands are where humanoid robots tend to disappoint. Most machines that look impressive in demos reveal the gap when asked to do something specific, pick up a misaligned object, apply variable pressure, or adapt grip mid-task. XPENG Iron has 22 degrees of freedom per hand. The human hand has approximately 27, but several of those are passive. At 22 degrees of freedom, Iron's hands enter the range where humanoid robot dexterity research says real fine motor tasks become achievable outside controlled lab conditions. Total body DRF, 82. That includes a flexible humanoid spine, a feature almost no competitor has prioritized. Spinal flexibility changes balance during dynamic motion, affects recovery under unexpected load, and alters the physics of bending and reaching in ways a rigid frame simply cannot replicate without adding compensating actuators elsewhere. We haven't gotten to the part about what's running inside XPENG Iron's head, and that is exactly where the earlier question about the battery starts to make a different kind of sense. Stay with this. XPENG Iron's sensor array is genuinely ambitious. 720-degree eagle-eye vision, a full spherical awareness system combining RGB cameras, 3D depth cameras, LiDAR, force sensors, and an inertial measurement unit. Humanoid robot technology explained at this level of sensor fusion is rare even in academic robotics publications. Most commercial robots pick 2 or 3 sensor types. Iron is running all of them simultaneously. The 720-degree claim deserves scrutiny. Standard humanoid robots achieve forward and partial peripheral vision. True 720, meaning full horizontal and vertical coverage with no blind spots, requires sensor placement and processing architecture that most teams don't attempt because the computational cost is high and the integration complexity is significant. If XPENG has genuinely achieved this, it solves one of the core problems in unstructured environment navigation. Things moving towards you from directions you cannot see. Full-body synthetic skin with embedded touch sensors rounds out the picture. Iron doesn't just perceive its environment, it feels contact across its entire surface. That changes the safety equation entirely when operating near humans. Three XPENG Turing AI chips, 2,250 to 3,000 TOPS of compute. A single high-end consumer AI accelerator card typically delivers around 200 TOPS. Iron is running 10 to 15 times that, distributed across 3 dedicated processors, all on board. The operating system is Tianji AIOS paired with XPENG VLA 2.0, a vision language action model. VLA architecture means Iron is not operating from a fixed instruction library. It interprets visual input, processes language context, and generates action in response to unstructured real-world conditions. The AI robotics future workforce question: whether robots handle novel situations without constant reprogramming, is precisely what VLA 2.0 is designed to answer. Connectivity is Wi-Fi and 5G. In retail, logistics, and manufacturing environments, real-time cloud inference can supplement onboard processing when tasks demand it. The hardware specification here is genuinely serious. Whether the software performs at scale under production conditions, only deployment answers that. The estimated price sits around $150,000 US. XPENG has not officially confirmed a retail figure. That number is an estimate, and it will move as production scales. The mass production target is late 2026. Here is the context that matters. China's humanoid robot development has accelerated dramatically in the past 18 months, with state-level support, deep manufacturing infrastructure, and established EV supply chains being redirected toward robotics. XPENG Iron versus Tesla Optimus is the comparison most Western viewers will reach for. But the more revealing comparison is XPENG versus the broader Chinese robotics field, where it is competing against Unitree, Fourier, and others. XPENG's edge is integration. They already build vehicles with full-stack AI, battery systems, and sensor arrays. Adapting that expertise to a bipedal platform is not a pivot. It is an extension. That is an advantage competitors building robots from scratch do not have. Back to the solid-state battery. The real reason it matters isn't runtime, it's regulatory positioning. Industrial facilities, hospitals, retail floors, and homes all carry strict rules about chemical hazards near people. A conventional lithium-ion robot faces friction at every deployment site. A solid-state robot removes that friction almost entirely. XPENG didn't choose solid-state because it was impressive. They chose it because it was necessary for the environments they plan to sell into. That is a company thinking past the demo stage. If this kind of deep technical analysis is what you're looking for, the channel is right here. The best humanoid robots 2026 will be remembered for aren't the ones with the most impressive footage. They'll be the ones who made it into real buildings, doing real jobs, without needing to convince anyone they were safe. XPENG Iron is engineered specifically for that outcome. Whether it delivers is the question this time next year will answer. The category is moving faster than the coverage. Keep watching. If you know someone still sleeping on what China is building in robotics right now, this is the video to send them.